For this lesson, we want to address some of the problems with the DUI table and expand it a little bit by looking at some additional reactions. Before we look at the additional reactions, let's go back and think about the DUI table and some of its deficiencies. So by the DUI table, what I mean is the table of the reactivity of alcohols. We have alcohols come in 4 flavors. You can have methyl alcohol, primary, secondary, and tertiary alcohols. They can react with either hydrochloric acid or hydrobromic acid, sometimes called hydrogen chloride or hydrogen bromide, depending on how technically accurate we want to be. Either one's fine. When we react an alcohol with hydrochloric acid, the only real useful laboratory reaction that we see is a tertiary alcohol reacting with hydrochloric acid via an SN1 mechanism. And this was the first mechanism that we looked at in Lesson 5A. In Lesson 5B, this past lesson that we're looking at right now, we started to fill in some of the gaps associated with hydrobromic acid. And we ran into this problem with secondary alcohols reacting with hydrobromic acid, and they have a tendency to undergo rearrangements where we have shifts. Methyl groups and hydride groups will shift over. So that's why there's an asterisk right there. And also, in this lesson 5B was the first time that we saw the SN2 reaction. The SN1 reaction typically involves the formation of a carbocation. Carbocations that are secondary can shift, so that's why we still see them right here. But primary carbocations don't typically form during the course of a regular chemical reaction. If you see a primary carbocation somewhere in your mechanisms, you've likely made a significant mistake. For these simple type of substitution reactions involving alcohols and halogenic acids, such as HBr, primary and methyl alcohols will undergo an SN2 reaction. And that's what we looked at here. And this SN2 reaction has the first step, which is the fast step, goes energetically downhill, and we end up protonating the alcohol. This acid-base chemistry is both fast and spontaneous, and then we have this very long, this slow second step where we have to convince 2 different ions to come together at the right place with the right orientation and undergo a substitution reaction. This SN2 reaction is overall spontaneous because it goes from a higher energy state to a lower energy state, but it's very slow simply because you have to wait a long time to get the ions to line up just right. In this next lesson, we want to explore, well, how do we deal with these 3 gaps right here? Is there any way of putting a chlorine on an alcohol that's methyl, primary, or secondary? And the short answer is yes. And then, is there a way to stop a shift from occurring? And the answer is yes. The key reagent that we use in order to put chlorines on primary, secondary, and methyl alcohols is a chemical called thionyl chloride. So this chemical reaction right here involves, among other things, there's an alcohol present on this chemical. This is an ester, which is a type of carbonyl group, functional group that we've not seen before, probably not seen before. And we're going to react this right here with thionyl chloride, and we're also going to add in pyridine. And pyridine is both a catalyst and a solvent. And by the time we explore the mechanism, hopefully you'll understand how pyridine acts as both a catalyst and a solvent. So here on a new clean whiteboard, we have our 2 reagents, and this reaction specifically is going to produce an alkyl chloride. So that alkyl chloride is going to take the place of the alcohol. This particular molecule is more complicated than many of the molecules that we typically show you at this level in organic chemistry, because we don't want to confuse you with all these different functional groups. I broke kind of that rule, and I'm confusing you with this ester because I looked up this reaction that somebody actually carried out in the literature to see that it's actually being done, and the answer is yes. It's not just something that we teach you, and that happens a lot. The general organic chemistry, we teach you a lot of chemical reactions that nobody uses in the laboratory anymore. So I wanted to make sure that we still use it. And these are the reagent conditions. So they added thionyl chloride and pyridine, and they ended up exchanging that alcohol, substituting it for a chlorine. In addition to the alkyl halide product that we want, getting a chlorine on in place of an alcohol, you also end up producing an equivalent of hydrochloric acid And by equivalent, I mean for every 1 mole that you start with, you end up producing 1 mole of hydrochloric acid and also sulfur dioxide. Both of these molecules are gases at room temperature under organic conditions, and that's going to become important later on. One of the tricks that we use in organic chemistry in order to make it easier to show our mechanism is we redraw the molecule using R groups where we don't want to show all of the atoms because they're not participating in the chemistry. So if you look at your starting material versus your final product over here, notice that the only thing that changes is the alcohol becomes a chlorine. So the rest of this doesn't participate meaningfully in any of the chemistry, so we're just going to re-represent this as R. And these 3 lines right here are a way of communicating exactly this, that I'm going to redraw my organic compound as something else, and this is that something else. So we see these 3 lines in organic chemistry as kind of a shorthand to say I don't want to carry around all of these atoms in my drawing. I'm just going to simplify it and call it an R group. And we're going to undo that at the end, and you'll see what I mean. Okay, so now that we have a more simplified version of our starting material that focuses specifically on this alcohol, now we're ready to think about how it's going to react chemically. The first step of the chemical reaction is the partial negative charge of the oxygen makes this oxygen a strong nucleophile. And here I have the full Lewis structure of thionyl chloride, which I think we've seen in a couple of example problems before. The sulfur of thionyl chloride contains a very significant partial positive charge, so the partial negative atom throws its electrons as a nucleophile into the partial positive electrophile, and then this sulfur is going to break the weakest bond. And this idea where a nucleophile attacks an atom that has a pi bond and then that pi bond breaks is the start of almost every mechanism that you show in the second half of organic chemistry. This is a very common feature where the nucleophile throws its electrons at the positive charge and then a pi bond breaks because the pi bond is very weak. And this is the end of the first step. Right? Hopefully already you realize that this is going to be much more complicated than an SN1 and an SN2 reaction. It's neither of those. It doesn't have that special type of name like SN1 or SN2. And so this is just called the thionyl chloride reaction, if it does have a name. The equilibrium does not favor the formation of this conjugate right here. When you add a Lewis acid and a Lewis base together and they just kind of stick together, that's called a conjugate. And this conjugate right here has all kinds of steric issues. You've just kind of crammed a lot of electron density around that sulfur, and equilibrium actually favors this thing falling apart, where this negative charge on the oxygen means that one of these lone pairs will slide back down again to reform that double bond, and it pushes off this oxygen right here. And we just go right back to where we started from. So this is an endothermic, non-spontaneous step, and the only way to get this reaction to work is to couple this with an exothermic step that pushes us through this problem point. So in a typical reaction flask, this conversion is happening millions of times, at least per second, and these molecules then immediately decompose back to the starting material. But very occasionally, one of these products, actually because we're not done yet, this is called the intermediate. This particular intermediate gets caught and pushed further down the chemistry. That's the next step of our mechanism. And this is the role of pyridine. Pyridine is a good solvent for reasons that we'll talk about later, and hopefully someday you'll experience in the laboratory. It does a great job because the nitrogen makes it polar enough to dissolve things that are slightly polar, and the rest of this aromatic ring system, this benzene ring-like looking thing, it does a good job of dissolving nonpolar substances. Not only is this the solvent, it also is a base. And so what the pyridine does is it rips that hydrogen off of the oxygen. And if you remember, an oxygen that carries a positive charge typically has a pKa in the ballpark of -2, meaning that it's a very acidic oxygen. And because it's very acidic, that's why equilibrium tends to either push this way or the base will come in here and grab this. And if pyridine is your solvent, then the probability of your solvent encountering this ion is very high. A solvent is defined as the thing that is in greatest abundance. So you've got a ton of this pyridine floating around. Even though this stuff only transiently forms and wants to decompose, the probability that the pyridine is able to catch it in a very exothermic process and rip that hydrogen off pushes this molecule through kind of this tricky spot. And we end up now with a stable conjugate right here that can't really go backwards at that point. Hey, the pyridine has pushed it through that decision point, and now we're at a useful, meaningful intermediate. And while this part of the molecule will change quite a bit, and the chalkboard problems are going to have you show this same mechanism for a much simpler alcohol. So you're going to change what's going on down here below the oxygen. Everything above the oxygen is the same every time you're asked to show the thionyl chloride mechanism. And we're not done yet, because remember, what ultimately we're trying to do is get the alcohol off and replace it with a chlorine, so we need to keep going. And again, none of these steps are steps that represent the SN1 or simple SN2 mechanisms that we just saw. This is a brand new mechanism, and it's not an easy one. The next step of the reaction involves the negative charge from the oxygen swinging down its electrons. Organic solvents really struggle when you have a negative charge, especially if that negative charge is concentrated on a very small atom like an oxygen. A negative charge on an oxygen is very difficult for a molecule to handle in an organic solvent. It's very high energy, unstable. And so if that negative charge on the oxygen can swing down to reform a bond, that gets rid of the negative charge on the oxygen and replaces it with a negative charged chloride. Now, chloride is actually easier for the solvent to deal with because it's much larger. It's what we call a good leaving group, and we'll talk about leaving groups later on. So at this next step, so we went started with starting material through the blue steps. That would be the first hump in our energy diagram, and that would be a big uphill climb. And then we have a little downhill slump, so this would be the next hump in our energy diagram. And then we have a very large downhill slide in this third hump in our energy diagram. And there's one more. So again, this is an odd mechanism. It does not bear similarities to SN1, SN2. You definitely want to memorize this mechanism as kind of a standalone thing that you've learned. And what you're going to find is that everything that goes on with thionyl chloride will start to seem familiar when you look at other reactions. So I'm not showing you SN1, SN2, and the thionyl chloride mechanisms because alkyl chlorides are that important. I'm showing you these mechanisms because they illustrate pieces of chemical reactivity that repeat in other situations. So you want to memorize this one. You want to kind of practice drawing it out, maybe make some flashcards. Fill up a notebook with your attempt at writing these mechanisms, just like a young child would practice handwriting. You guys have to practice mechanisms like that. Or do it when you need to retake the course next semester. It's up to you. Next step of the mechanism is weird, and this really doesn't have many similarities, and experimentally it took them a while probably to figure this out. This chloride ion will come in here and just push off the oxygen and everything that's attached to it. So if you kind of ignore these two purple or magenta arrows right here and just focus on this one for the time being, this is where we end up with the alkyl chloride. But if we're going to show the correct mechanism, we need to know those other two arrows. And we're used to seeing chlorides kind of pop off, at least off of a hydrogen and an acid, and this is pretty common. We just saw it over here, but this is different. This is a case where a bond actually swings over. So the sigma bond between this carbon and this oxygen just kind of slides over into a pi bond, and you'll see that pi bond show up in your final product, which I've also drawn right here. This sulfur-oxygen double bond is already there, and now we just made a brand new sulfur-oxygen double bond right there. The chloride pops off, and we end up going from one molecule to three molecules. Now, I don't know what the energy diagram for this reaction looks like. You're not required to know what the energy diagram for what this reaction looks like. As far as the rate determining step goes, it's probably this step, and then this is also kind of a close call. So this is a difficult reaction. It's not that it's endothermic, it's that you really have to go uphill in energy because you got two molecules coming together at the same place and the same time, and very similar to an SN2 reaction. So these right here, I see 1 and then 2 and 3, 4 steps are the key steps in the mechanism. So one of the ways to remember the thionyl chloride mechanism is to remember that it has 4 steps. And then You got to know what the 4 steps are, but at least knowing how many steps there are reduces the probability that you completely screw up. When you are asked to show an organic chemistry mechanism, it is not required for you to show the formation of these inorganic products. So your mechanism could exclude the sulfur dioxide and the chloride ion, and you still would have the correct mechanism. Organic chemists really only care about the story of the carbons. These are not carbons, they don't have carbons, and so if you didn't bother to show what happened to them, nobody would even notice. The reason that I'm showing you what happens to them is just for the sense of closure, that if sulfur dioxide and hydrochloric acid are products of this reaction, which we normally wouldn't bother to show, well, how do we get them? Well, this is how we got the sulfur dioxide, and you'll notice that we produced chloride, but we have not yet produced hydrochloric acid. So I'll come back to that in a second. But first, the sulfur dioxide is a gas at room temperature. And because it's a gas at room temperature, that means that it floats away. As it floats away, that means that it's no longer able to undergo a reverse reaction. This is an example of Le Chatelier's principle. If you drive off one of your products and remove it from equilibrium, then your reaction will always be trying to fill that gap, and so it never achieves an equilibrium. Producing a gas product is actually a really useful way of pushing the equilibrium all the way over to the side of the products and getting as close to a 100% yield as you can usually get in an organic chemistry reaction. This chloride ultimately needs to become hydrochloric acid. And all of these steps are inorganic, so this is more to explore a tangent of curiosity than it is to learn the actual organic mechanism. But there's 2 loose ends here. First of all, how does the chloride become a hydrochloric acid? And second, I call this a catalyst. Pyridine is a catalyst, and yet, if you look at the reaction as we've described it so far, the pyridine is going to pick up that hydrogen, and if the pyridine picks up the hydrogen, then it's going to look like this. And so a catalyst is something that does not get consumed during the course of the reaction. And if we don't take that hydrogen off of the pyridine, then we're lying when we call that thing a catalyst. And so the final step from an inorganic perspective is that the chloride ion will come over here and rip that hydrogen off, and we'll reproduce our catalyst so that it can be used again in the next reaction, and this is ultimately where we get hydrochloric acid from. Equilibrium does not appear like it would favor the products. Hydrochloric acid is a strong acid. This is an acid-base reaction. You would definitely expect equilibrium to favor the reactants in this case. And that's true. This reaction happens very slowly, only occasionally, but when it does happen, the hydrochloric acid outside of water, which is how we run organic reactions, we don't like to put these things in water, this will be a gas and it will float away, and through Le Chatelier's principle, ultimately it will force the reaction to continue until the chloride ions have eventually ripped the hydrogens off of the pyridines, this is called pyridinium, to reproduce your pyridine. So the hydrogen chloride that's produced in this reaction floats away as a gas and further drives the equilibrium. If you blinked, you might have missed that I actually redrew out my final product in all of its glory. So in the same way that you use these 3 lines to say, there's a lot of stuff here I don't want to have to draw as I'm walking through this mechanism, when you're done, it is good form to then undo the R group, to go back and state explicitly, okay, now that I'm done, remember that this is what my R group looked like, and then I have shown my final product. And this is kind of good manners as an organic chemist for you to do that when the reaction is over. So as far as showing a complete electron pushing mechanism for this reaction, it would be, you don't have to show everything that I have on this slide. You just need to show up until you get to this magenta product. These black inorganic products are not critical in the showing of the organic mechanism. You actually don't have to show good manners by redrawing your compound in all of its glory. You could just show these 1, 2, 3, 4 steps, and that would be a suitable answer. A bit rude, you've shown bad manners by not redrawing out the original starting compound, but it would work. People would know what you were talking about. Next mechanism. So remember that I wanted to show you thionyl chloride and another problem. So let me try that again. Hydrochloric acid leaves these 3 noticeable holes in the DUI table. What we're going to do now is start to address those holes by adding thionyl chloride as another column on this DUI table. Okay? DUI is just me being funny because, not that I think driving under the influence is funny, but if this is an alcohol table, then we'll just call this the DUI table. Somehow it feels shorter. All right, the thionyl chloride directly fills in those 3 gaps. There is a problem, though, when you have a tertiary alcohol. Thionyl chloride, in the last step of the mechanism, the chlorine has to come into this carbon right there. And if this carbon is tertiary, then sometimes it's a little bit cluttered. There's a lot of carbon, a lot of electron density, and the chloride ion has a hard time making it into that position. They call this sterically hindered. So tertiary alcohols are going to have a hard time reacting with thionyl chloride, which isn't a problem because then we use hydrochloric acid, and so we just use the thionyl chloride to kind of fill in these holes. PBr3 addresses primarily this issue right here. Secondary alcohols have a tendency to shift when you react them with hydrobromic acid. PBr3 does the exact same chemistry. It replaces an alcohol for a bromine, but it does not allow a shift to occur. So in the next mechanism, this was the reaction that we looked at in the previous lesson, where we had this would be 3-methyl 2-butanol was reacting with hydrobromic acid. We protonated the alcohol in the first step. The second step is the formation of the carbocation, and this is just the classic steps you see in a typical SN1 reaction. And if you weren't careful, you would then bring your bromide ion into that carbocation and think you were done with confidence that you have the correct answer. And what you failed to account for was that this is a secondary carbocation that is derived from a secondary alcohol. In the DUI table right here, secondary alcohols have a tendency to shift if there is a neighboring option that allows that alcohol to become a tertiary carbocation. And we saw this in lesson 5b, that the hydride will shift over and that moves the carbocation to a more stable position. And this shift right here is easy and it's spontaneous. So anytime you see a secondary carbocation, you need to look over both shoulders to make sure that there's not a tertiary position lurking off to the side. It always reminds me of The Walking Dead, that you got to watch out for zombies all the time. Once this secondary carbocation has shifted because the hydride moved over to fill the hole, now you have a tertiary carbocation and the bromide comes in and we end up with our rearranged carbon, our rearranged product. And it's rearranged because the alcohol started off in this position, but in our final product, there's a bromine at a different position. So this is a classic rearrangement reaction. PBr3 does not go through a carbocation. And so since it does not go through a carbocation, when you react this alcohol, that same starting material alcohol with PBr3, the final product is going to show the bromine at the position where the alcohol is. There is no rearrangement. And so it does not shift. The mechanism for PBr3 is variably shown incorrectly almost all of the time. And so the mechanism I'm going to have you learn, it's incorrect. Let's call it oversimplified so we feel better about the quality of our educational experience. But this is not quite what happens, but it's close enough. The alcohol, PBr3, is phosphorus tribromide. The alcohol will react. This is a partial negative charge, pushes into the partial positive of the phosphorus. Just like where the thionyl chloride mechanism showed an alcohol pushing into a sulfur, this PBr3 mechanism shows the alcohol pushing into a phosphorus. In one step, that bounces the bromide off, and we have our first and only intermediate. This is straightforward SN2 reaction. So in fact, the mechanism for PBr3 is just back-to-back SN2 mechanisms. So that SN2 mechanism doesn't only apply when you're reacting primary methyl alcohols with HBr. We actually see the SN2 mechanism show up in other places as well. This PBr3 mechanism is like SN2 squared. And I used to call it that, but that's not technically correct because we're not actually showing you the right mechanism. But for the sake of you learning the bare minimum in order to survive this class, you can call this an SN2 squared mechanism in your notes, but I'll ask you to draw it out, and you can draw it out in this way. The alcohol pushes the bromine off, and then the bromide kind of returns the favor and bumps the oxygen off of the carbon. It's almost like it sets it up and then smacks it in the back of the head. And we end up with the bromide right here replacing the alcohol exactly where the alcohol was with no shift occurring. Notice the difference between the two products. When we added HBr, the alcohol produced a carbocation, and then a shift causes the bromine to show up where there are two methyl groups. Do I have the wrong product? I do. Shoot. I need to fix that. All right. Hopefully your notes look a little bit more coherent now. I forgot about the law of conservation of matter, to my shame, and had an extra methyl group originally right here. In the final product of this reaction, there are 1, 2, 3, 4, 5 carbons, and the bromine is attached to carbon number 2, and there's a methyl group attached to carbon number 3. If we had just used HBr, there's still 1, 2, 3, 4, 5 carbons, but now both the bromine and the methyl are attached to carbon number 2. So HBr causes a shift, and PBr3 allows us to avoid that shift. This right here, in its entirety, with the correct number of carbons as opposed to what was there before, is the answer to this right here. Show a complete electron pushing mechanism for the reaction of 3-methyl-2-butanol with PBr3. So that was the mechanism that I showed you right there. So now we're ready to finally kind of complete this question. How do thionyl chloride and phosphorus tribromide address deficiencies of the DUI table? Well, it's shown here in the chart, but let's put some words in here. SOCl2, or thionyl chloride, as a chemist might call it, allows methyl primary and secondary alcohols to react to be converted to alkyl chlorides. So that's the first step. And then PBr3, or phosphorus tribromide, in the words of a chemist, allows for secondary alcohols to become alkyl bromides without shifting, without those types of carbocation rearrangements or shifting. PBr3 will also work for primary and methyl alcohols as well. And so if you don't like the HBr SN2 mechanism, you can show two SN2 mechanisms by showing the mechanism for PBr3 and on methyl and primary alcohols. And on an exam, there really isn't a difference. For these two rows of the periodic table, it does not matter if you use HBr or PBr3. For this row of the DUI table, it does matter, because secondary alcohols have a tendency to shift. If you want a shift to occur, then use HBr. If you want to avoid that shift, then use PBr3. If there's no reason for the secondary carbocation to shift, because it's not surrounded by tertiary positions, then you can use either one. For tertiary alcohols, we want to stick with the acids, HCl and HBr. Both thionyl chloride and PBr3 have some steric issues with tertiary alcohols, and they don't work as well. So now you have quite a few choices. And on the chalkboard problems associated with this assignment, you'll notice I'm going to ask you for a bunch of mechanisms. You don't need to draw those out. And I would encourage you, before you start that mechanism, to identify if the alcohol is primary, secondary, or tertiary, and then identify the reagent that you're adding it to, SOCl2, HBr, TSCl, we'll talk about that in a second. And then first identify, well, what's the mechanism that the DUI table should tell me? Failure to know how to use the DUI table is one of the problems that students experience on the next exam. On a write-on exam, we'll actually see them in perfect detail write out the DUI table and even put some helpful notes off to the side of why they're using it. And then they won't know when to apply it to the different practice questions. And so these 5 questions here are intended to allow you to practice applying the table to the homework as you're going through it. This last point, question number 4, asks for us to show the mechanism for the reaction of S2-butanol with tosyl chloride. It doesn't fit in the DUI table. And in fact, it probably fits better in the next chapter, but we're almost there, so let's talk about it. This Tosyl chloride is a different reactant than we've seen before. And it represents a case where chemists start to get really lazy in terms of how they show Lewis structures. So this right here is Tosyl chloride. Technically, the correct name for it is 4-methylbenzene sulfonyl chloride, which is actually kind of a mouthful. The common name for this is toluene sulfonyl chloride, and that makes a bit more sense. This toluene is a benzene ring. That's what this thing is, the 6-membered ring with alternating double bonds. That's a benzene. If it has a methyl group on there, it's called toluene. All 7 of these carbons collectively become toluene. Sulfonyl is sulfur with 2 doubly bound oxygens. It's the sulfur equivalent of a carbonyl, where the carbonyl just has 1 double bonded oxygen. Sulfonyls have 2, and all of that's attached to a chloride. And so even toluene sulfonyl chloride, which would be really helpful for chemistry students to hear those words, because that actually allows you to kind of unpackage the structure, is further abbreviated to Tosyl chloride. And I think the justification for that abbreviation is they grab the T and the O, they grab the S, and they grab the Y and the L, and they called it Tosyl chloride. And the Tosyl chloride just gets abbreviated as TSCl. And so mechanistically, again, I'm going to show you another mechanism that is oversimplified and technically wrong, but organic chemists use it often enough that if you show this mechanism in the way that I'm going to teach you, you can get by as an imposter. People won't know that you're not an expert organic chemist, because even expert organic chemists get really lazy with this Tosyl chloride compound. And what it does is it is a way of taking an alcohol and turning it into a fake alkyl halide. And I'll explain that in a second. Let's first just kind of look at the beauty of the mechanism. This mechanism is exactly the same as everything else that I've shown you today, in that the alcohol oxygen is going to toss its electrons at the electrophilic atom, in this case the sulfur. But because chemists tend to just abbreviate all of this as TS, this whole thing on the right-hand side over here, then you just throw it at the TS, you pop off the chloride, and you've linked the oxygen through the sulfur to this Tosyl group. You're not quite done yet, because you've got a positive charge, and that creates a bunch of problems for our solvent, so we need something to come along and rip that hydrogen off. You can use the chloride ion that just came off. It'll pull that hydrogen off, or a lot of times they'll run this reaction in pyridine, and the pyridine instead will pull the hydrogen off. It does it better. It's also the solvent, so it's everywhere. And eventually, if somebody asks, well, what happens to the pyridinium, which is that nitrogen once it picks up a hydrogen, then you can say that the chloride goes ahead and removes that hydrogen. So mechanistically, if pyridine is present, you want to show pyridine ripping that hydrogen off. If nobody bothers to specify if there's pyridine or not, then the chloride will do the job in a pinch. And we're to our final product. And a lot of times they don't even put a space between these. It's just OTS. And that's what they refer to as a tosylated alcohol. Now, the reason that we tosylate the alcohol, there's 2 reasons you do that. First is an alcohol has a tendency to act as an acid because of this hydrogen right here. And it does it at times you don't want it to. And so sometimes what chemists will do is they will tosylate an alcohol so that they hide the alcohol. It's no longer acidic because that hydrogen's been plucked off. And then if you just add aqueous hydrochloric acid, you'll undo the tosylation, push the equilibrium back the other direction, and you'll go back to the alcohol. It's what they call protecting an alcohol. And it usually is when a chemist has an alcohol on one portion of the molecule they don't want to mess with, but there's something else on the other side of the molecule that they need to convert to a different functional group. And so they hide the alcohol by tosylating it, and then they unhide it later on by just clipping that tosyl group off. And we'll do that later on. For now, we're going to use tosylation to take an alcohol and convert it into something that behaves just like an alkyl halide. So even though there's no halogens present anywhere in this compound, we'll see in the next few chapters how a tosylated alcohol, this compound right here, will actually do all of the chemistry that an alkyl halide tends to do. And so it's a way of converting an alcohol into an alkyl halide without actually converting it into an alkyl halide. And why would you ever want to do that? Well, we probably don't answer that question ever to anyone's satisfaction until you get to advanced courses in organic chemistry. So, in many times in organic chemistry, if you want to know, well, why do I have to learn this and what am I doing this for? It's kind of a Karate Kid moment where you paint the fence, you wax on, you wax off, and then later on, you're this amazing karate guy or girl, whatever. The analogy fell apart, and I'm done. All right, let's go back to the lesson and make sure we filled in all the blanks. So that mechanism for the reaction of S2-butanol with tosyl chloride, you'll need to show that in the 2 steps that I just showed you on that PowerPoint. Here's the table that you want, and then the other 2 mechanisms are derived from that PowerPoint as well. And I'll post that PowerPoint as well with the lessons so that you can just copy those mechanisms down. And again, you want to practice drawing out those mechanisms. And even if it seems like, yeah, I know this, you don't. You need to practice those mechanisms so that you can show them perfectly, because they're easy to learn when there's just a few of them. And as the course progresses and the pile of mechanisms that you're responsible for gets larger and larger, you don't want to have to cram 18 of them into your head the night before the exam. As far as the chalkboard problems go, there are the bottom 5 right here, which are just mechanisms, very similar to the ones that I showed you in the lesson today. I do have one question about IR spectroscopy, and so your job is to go back to the lesson on IR spectroscopy, figure out what kind of peaks you would expect to see for 2-butanol, figure out what kind of peaks you would expect to see for 2-chlorobutane, and then looking at the peaks in the spectrum, try to figure out which of those 2 compounds this spectrum corresponds to, and then provide your rationale.